So in this first example, we're going to do a trigonometric substitution in which x is going to turn out to equal 4 times the sine of theta. So here's the integral we're interested in evaluating. So we have the integral of 4 over x squared square root of 16 minus x squared. And this is a dx. And what we want to notice is that we have a difference of squares underneath the radical sign, which indicates to us that a trig substitution is possible and may or may not be helpful. So if I set up a right triangle with angle theta, and I look at this, I have a difference of squares. So remember that the hypotenuse squared equals the sum of the squares of the legs. So if I have a difference in squares, then one of the two legs has been solved for. So for example, I could write h squared minus leg 1 squared equals leg 2 squared. You wouldn't typically do this. I'm just trying to drive home the formatting here has us in a position where a difference of two squares indicates that 4 squared, which is 16, indicates that 4 is going to be the hypotenuse of my right triangle, and that x, the other value that's being squared, is going to be one of the two legs of the right triangle. And I get to choose which leg I assign it to. I can put the x here or here. So in this case, because we have the form hypotenuse squared minus leg squared, I know that the hypotenuse would be 4 if I'm converting from rectangular coordinates into trigonometric coordinates. So hypotenuse is 4. One of the other two legs will be x. I'm going to go ahead and assign x to the side opposite my angle theta, and that means that this guy, you take the square root of both sides, you have the length of the other leg. So the square root of 16 minus x squared indicates the length of the side adjacent theta. So that's first step, is you take your element or term that looks like it has integrated a form coming from the Pythagorean theorem, and you construct the right triangle that would go with it. And this is a skill that you would have done first in a trigonometry class. And then what you do next is you find the elements in your integral that correspond to the right triangle, and you substitute things out. So for example, here I have 4 over the square root. So that would have the form hypotenuse over adjacent. So and hypotenuse over adjacent is going to give me a secant. So in this case, using this right triangle, what I see is that the secant of theta is going to be equal to 4 over the square root of 16 minus x squared. I can also see here, if I want to think about this as being a 1 times 4, I have a 1 over x squared. So the easiest place to get that from is going to be looking at it from this perspective. I have cosecant of theta. Here's theta. Cosecant of theta would be the hypotenuse over side opposite. And to get a squared down here in the denominator, I could square both sides of this. So cosecant squared of theta equaling 16 over x squared. So if I multiply both sides by a 16th, I wind up with 1 over x squared. So the 1 over x squared right here could be replaced with the 16th of the cosecant squared of theta. And the last thing to do is to deal with the dx. And to deal with the dx, I usually get the simplest relationship I can out of the right triangle. So for example, in this case, I can see that the sine of theta would evaluate very easily. The sine of theta would be x over 4. If we multiply both sides by 4, we get 4 sine theta equals x, and that's using my substitution for x that I have up here in the slide title. X in this problem is 4 times the sine of theta, so a conversion from rectangular coordinate into trigonometric coordinate. And then I use this in order to come up with my dx. So we take the derivative of both sides. We find d theta dx. So 4 times the derivative of the sine would be the cosine of theta. But this would be an implicit differentiation, so I would need to multiply by the derivative of theta with respect to x using the chain rule. So times d theta dx equals the derivative of x is 1. And then I could multiply both sides by dx. So we would get 4 times the cosine of theta d theta equals dx. So dx can be replaced with 4 cosine d theta. And now it's just a matter of going into the integral and making the appropriate substitutions. So I go into my integral. 4 over the square root of 16 minus x squared is, in trigonometric world, the secant of theta. So I multiply secant of theta. 1 over x squared is the same as a 16th times the cosecant squared of theta. So 1/16, the constant can pull out front, times the cosecant squared of theta. So that takes care of my 1 over x squared. And then the dx in d theta world is going to look like 4 cosine theta d theta. So 4 would factor out front, and then we would be multiplying by cosine theta d theta. So now I've completely converted from an integral involving dx over into an integral in terms of theta. Now we want to notice that order of multiplication doesn't matter. So we're okay to multiply the secant of theta times the cosine of theta, because multiplication of trig functions is going to be both commutative and associative. And secant is just the reciprocal of the cosine function. So the secant, which is 1 over the cosine, the secant times the cosine equals 1. So we get 1 times the cosecant squared. So simplifying this fraction out here, so we're going to get 1/4 of the integral of just the cosecant squared of theta d theta. And then what we want to recall from first semester calc is that if you take d theta of the cotangent of theta, you get minus the cosecant squared of theta, which means the cosecant squared of theta, if I multiply both sides by -1, the cosecant squared of theta is going to be the opposite of the derivative of the cotangent. So when we integrate the cosecant, we're going to get 1/4. We'll get a negative sign. We integrate secant squared. That's a horrible, or cosecant squared. I think I lost my c. We get 1/4 times the cotangent of theta plus the constant of integration. And then what we need to do is convert back into rectangular world, because we started in rectangular world. So we go back to our triangle and say, hey, from this triangle, what does the cotangent of theta look like? Well, cotangent is going to be adjacent over opposite. Cotangent of theta is adjacent over opposite. So we make that replacement for cotangent. We say -1/4 times the adjacent over the opposite, adjacent over opposite plus our constant of integration. And we have found our integral. We're done at this point.